So what's the difference between machine learning and deep learning? Well, most will say nothing, that deep learning is just a natural expansion of machine learning. And I agree with that. It's just sort of a more complex machine learning, more complex algorithms, more complex architectural structures, uh, more complex coding, more complex mathematics. That's all. You can think of it as going from basic SQL work into far more advanced neural networks. And namely, that is what is the difference, is the greater use of neural networks or AI structures that use machine learning elements for more complex work or complex goals. Basically, the machines are mimicking the human use of probabilities and pattern recognition and stimuli response, etc., in day-to-day cognition and response to stimuli. That's how we move through our day. Now, many will say that neural nets are patterned after human brains, but the truth is they were inspired by human brains. So we talked about simple elements of learning and machine learning, and now we'll review more advanced learning, or the move toward human level learning and cognition. The move is like going from a toddler machine learning to kid machine learning. For example, using classification to solve problems. This involves understanding deeper context. And this is the point in AI development where representation and abstraction of higher context, such as features, emerges. Now, features are fundamental to both the engine of deep learning, or neural nets, and human learning and perception. Features equals the value of nodes, and nodes are the intersection of representation, i.e. classification, and value. Now we'll see that in matrices. We'll see these intersections between features and the entities which they represent. Now, deep learning neural nets discover the connections between features/values and goals, and they do so by themselves. They learn. The more general the goal, the more general the AI, i.e. picking up a cup versus picking up something in general. So obviously, if I train an AI to pick up a cup, it's not going to be quite as valuable as if I train an AI to pick up anything, and then I can just specify what that anything is. Now that is the move towards artificial general intelligence. Deep learning is state of the art in AI right now, but there is a constant war between resources and optimization. Precision requires more data and more structure, which requires more resources and takes longer to optimize. Well, this may seem like the path to general AI. More structure is often too precise, and we call that overfitting. And it wastes dollars and resources. And we sacrifice efficiency, such as response speed. Speed is very, very critical in stimuli response. You can think of autonomous driving and a child running out onto the road chasing a ball. You need very, very quick speed in response. Currently, AI devs seek a balance between data and compute. But today, everything is driven by competition between companies and governments, and less precise open source is actually winning the race. But we'll get to that a bit later. So the dollars are pouring into AI resources, but only in very specific areas and where value can be determined. Now, ChatGPT supposedly spent $10 billion, and that's not surprisingly the amount Microsoft gave it, for training on 175 billion parameters. And now they want to go to 1 trillion parameters, and that will cost somewhere is estimated at around 50 billion, but I don't think that's accurate. I think it's a lot less than that, especially as the open source are showing us how to do it. So big money and big resources for the right areas. There are some huge opportunities for the rest of the decade in this area. The bad news is open source does it at a fraction of the cost with less precision, and you can download something equivalent to ChatGPT onto your phone and use it. Now, the building blocks of deep learning are neural networks, which are inspired by the human brain. There are various types of neural network architectures used for various specific purposes. They all seek to move from input data to output data of some sort driven by some goal. Now, usually a prediction, i.e. data, images, response, but not always. A falsification or noise can be produced inside of a generative adversarial neural net. So it's not always just straight up prediction. There are generative neural nets, obviously, generative AIs that produce outputs such as images. But if they use probability weights, then they are predictions, or what we call anticipations. We, the user, anticipate something, we give it a prompt, and the machine uses probability weights to give us its best guess as to what we're looking for. And we humans use anticipation constantly, even right now. You are all constantly anticipating the next 10 seconds because you believe it's going to continue on just as the previous 10 seconds. And that's how we instantly react to variance and stimuli as humans. We are in a constant state of motion or flow or transition from preconception to post-death. Now, life for humans and AIs is a constant flow or stimuli response, which is what neural nets seek to comprehend and master. Neural net inputs are data, or more accurately, real-world data representations that a machine can understand, usually in the form of matrices of values or vectors for intersecting features, columns, of an entity, lines. Each feature has a starting value, and the neural net iterates to improve the value to achieve the goal. In ChatGPT, the matrix, the entity and features, are words, and the intersection is a summation of proximity to other words. And now for context, we're starting to move into what's called dimensional multi-angulation, but we're not going to discuss that in this particular. Well, we'll discuss it a little bit later in the next future sections, but that's more for the dev bootcamp. The output data is a prediction, goal, or subset of input data, or representation and weights, or i.e. probabilities, adjusted by supervision. The key to do all this is creating great representations of real-world data into something a machine can comprehend and setting a good goal. The rest is relatively easy, so this is what we're going to do. When we set up these neural nets, we take a look at the real-world data, we set it up in a representation for the neural net, and that representation is supposed to lead to the attainment of the goal. The key to do all this is creating goal representations of real-world data into something that the machine can comprehend. So the rest of it is relatively easy. Now we need a goal to move the machine, just like humans need a goal to move throughout our day. And our number one goal is survival, and then all other goals in our lives sort of relate back to survival. The ultimate output of any neural net is an optimized matrix of weights that it then uses to make other decisions and to respond to stimuli. Now, success depends on good input data, good representation, and good goal setting and feedback of some sort. Doesn't necessarily have to be human. Could be reward, could be automated reward, could be another AI, but it needs that feedback to know how close it is to its goal. There's many types of neural networks. CNNs, or convolutional neural networks, they're used in image recognition and computer vision for autonomous driving. RNNs, recurrent neural networks, used in chat AI. GANs, or generative adversarial neural networks, or generative networks, and then when you add another one opposed, it becomes an adversarial neural network. And that's used in image rendering like DALL-E, so generative neural nets. Generative adversarial neural nets are used for generative enhancement and precision, like deepfakes, like creating deepfakes and understanding deepfakes. Now, all have their uses, and many are linked together in structures to achieve more complex goals. The key here is the use of weights, or more accurately, probabilities, at the connection points between neural nodes. Now, humans do the same thing when we make choices. We carry probabilities in our heads without knowing it, and use them to process and respond to the stimuli from the world in relation to our own goals. I can pretty well ask you about any perception in relation to a goal, and you can give me some sort of probability, i.e. on a scale of 1 to 10, related to a goal that you perceive, whether I gave it to you or it's in your own head. I can say, how close are you to your goal on a scale of 1 to 10, and you can probably give me a pretty good answer. While the features and their values are carried in matrices, so are the weights, and we use matrix multiplication extensively in current AI neural networks. In fact, it's matrix multiplication that is the bottleneck driving Google et al. To make TPU tensor processing chips and NVIDIA to make faster AI chips. They want to improve this matrix multiplication. That's the whole goal, is to make faster AI chips and therefore faster AI. Where are deep learning neural nets used? Well, they're used in facial recognition, and you'll run into these facial recognition machines at every airport when you cross a border, or even I ran into one trying to get on a plane to fly to Canada. It was straight up facial recognition just to get onto the plane. It's used in natural language processing, autonomous driving, generative models, we'll talk about these a bit later. Reinforcement learning, that's using rewards and punishments to train the AI. Note that the training phase is one stage with lots of resources needed, but once the network is solved, i.e. the weight matrix is determined or set, the implementation is much lighter. You don't need a supercomputer once you've completed the training and you have the weight matrices. Now, it's the weight matrix that's the real value. At that point, you can run it on your phone. It's that light, not small. Now, this all depends on the design of the AI. There's currently a big drive for efficiency because the next step is deep context, which needs exponentially more resources and dollars. So let's go a bit deeper into some types of deep learning neural nets. So feed-forward neural nets are simplistic neural nets, often used for classification and basic pattern recognition. And again, we'll go into all these further ahead in the presentation in other sections. We'll go into these quite a bit deeper. Convolutional neural nets, we talked about that before, uses a convolution layer to break apart images into smaller pieces to apply multiple neural net layers that activation, and pooling before producing a classification output of what it sees. So it's used in computer perception. This is where we tend to use these convolutional neural networks. This is then used in other functions like driving response in autonomous cars, etc. Long short-term memory, LSTM, is really about attention and context. We see it in natural language processing, so some chat AI systems, but it's a bit out of date over some newer methods. Autoencoders are used to map large representations into smaller ones in an act called dimensional reduction. All of this is used in contextual layering like we humans do, managing and generating deep context like sarcasm or empathy or creativity. So GANs use generative techniques in a competitive model. That's adversarial. So there's generative neural net and then there's a generative adversarial where you have a couple. Now, generative techniques learn the underlying distribution of data and models to regenerate the input data. That's what their goal is. Adversarial, in that when another neural net layer, a discriminator we call it, determines if the output of the generator, which is another layer, meets a generally opposing goal, i.e., is it real or is it fake? Now you can see how this would work if you had one neural net layer trying to identify fake images and another neural net layer trying to generate the very best fake images. You can see how they would be pitted against each other to improve the output of both. That's how we got deepfakes. Computer vision primarily uses CNNs for comprehension and generative and neural nets for stimuli response. NLP image AIs, so this is like DALL-E or Hugging Face, primarily transformers and feed-forward neural nets and generative neural nets for the response. So these things all layer together. That's the whole point. All new advanced AIs use combinations of neural nets to get things done and to advance deep learning. Although at this time it is down to training on successively larger models. Although some of the giants of tech are sort of now having their AI lunch eaten by smaller open source startups and their smaller training sets of data. And they're realizing that the variance between themselves and these open source organizations and startups is not significant enough to stop the bleed. And they're realizing that the difference between the two systems is not great enough for the average, person. They're not going to notice too much of a difference. And this is a big problem for the big tech companies. It's another one of those precisions is overrated moments and a mea culpa. It's basically saying, once again, yeah, you can use these gigantic models and create high-level precision, but once you've got the weights, you don't really need that large a model to get the job done because, frankly, even as humans, the vast majority of us do not use the entire extent of the human language to communicate. We use a subset of it. So deep learning is growing and infesting the entire world, especially as open source versions of chat and image AI roll out. And these new startups create new tools and plugins and plugins to their own software. Some companies are doing that as well. So now in the next section, we're going to start going deeper into some of the mechanics of everything we have discussed up to this point. Starting with data and pre-processing. So we're 32 slides down. There's 105 more to go. This is a marathon, and we're going to get far deeper into the details of this stuff. And you're going to get some hands-on training as well in the labs. And like I said, we'll have other things like a Q&A a panel of experts, far more expert than I am in the details of the design, details of the coding. And we'll have a Q&A session, a panel Q&A session, where we'll have individuals who are coders and developers, so you'll have a lot more detailed information into how these things all sort of go together.